morning, everyone. Welcome to this tutorial on decision diagrams for optimization. This is the first of a two-part tutorial, and the second part will be later in the morning. It'll be given by Willem-Jan van Hoeve, who's right here. Both tutorials are self-sustaining, I believe, independently. So let me say a word about decision diagrams to begin with. I'm sure you've heard of them. They've been used in computer science for a long time, mainly for logic circuit design, logic integration. But it turns out that they are a useful tool for optimization. So that's today's topic. Now, how does this relate to this conference, planning and scheduling? Well, I think the main way it relates is that decision diagrams are well suited for dynamic programming formulations of problems. That is to say, recursive formulations in which you have a state space, and the actions and costs are state dependent. So this is the way that planning problems are very conveniently formulated. So I think it's a natural approach to planning and scheduling. It turns out that decision diagrams also provide an alternative strategy for defeating recursive dimensionality in dynamic programming. So this is the problem that arises when the state space grows exponentially. So what, they solve the problem by branch and bound, somewhat analogous to integer programming solvers. So it's a different strategy for dealing with this task of searching the state space. Okay. So decision diagrams have been used in planning and scheduling literature, mainly to encode costs, cost functions, cost-to-go functions, state-dependent costs. In fact, there was an excellent tutorial yesterday on this topic. I assume that the video will be posted at some point. See the tutorial if you missed it. This approach that I'm describing will be different because it uses decision diagrams as a general framework for optimization as opposed to a technique for encoding costs and cost-to-go. Somewhat different approach. Okay, so what are the advantages of decision diagrams? Well, you got to keep in mind that we are competing with 50 years of technology in discrete optimization, mainly in the form of integer programming. So we have stiff competition out there. But I still think that there are advantages. One is that traditional math programming requires inequality formulations. Decision diagrams don't care whether it's inequalities. They don't care whether the problem is linear or convex, or whether the relaxations are linear or convex. As I mentioned, you can solve DP models in a different way. It turns out also decision diagrams parallelize much more effectively than math programming algorithms. And finally, they're very conducive to post-optimality analysis, which I won't talk about today, but it's an interesting aspect. Now, the downside is that so far the technique has only worked for discrete optimization, deterministic problems, although I think they can be extended. That's ongoing research, which I won't say much about today. Okay, so this is what I'd like to talk about. And of course, the floor is always open for questions or comments as we go along, so I can follow your interests. This is the basic outline. So I'm going to give you a brief introduction to decision diagrams, and we'll talk about how they can be used to solve optimization problems as an exact representation of the feasible set. And then we'll move into a more practical approach that uses relaxed decision diagrams. And I'll show you how to model problems and so forth. How the problem can be solved by branching down. Show you some computational results. And then we'll talk about modeling the costs in the problem and show you how the problem can simplify radically. And then as time allows, I'll talk about an extension to non-serial dynamic programming and non-serial decision diagrams, which expands the scope of this approach. And finally, there's some references attached to these slides, which are already up on the conference website, I think. Have a look at those. Okay, so that's the plan. Decision diagram, of course, encodes a Boolean function. It goes way back to the 1950s. So as you probably know, we can set x1, for example, to 0 or 1 and take the branch accordingly. And for any given set of values for the x1, 2, and 3, we follow the corresponding path to the diagram, and the terminal node indicates whether the Boolean function has value 0 or 1. So it's a nice way to encode a Boolean function. As I mentioned, they're used for circuit verification. You can, for example, you can verify a circuit by encoding the circuit as a decision diagram, and then you encode the logical function you wish to implement with that circuit with a decision diagram, and check to see whether the two diagrams implement the same function, whether you're equivalent. And you can check that, it turns out, easily because there is a unique reduced form of a decision diagram, and you merely reduce the two diagrams and check to see if they are identical. Okay. Unfortunately, there's a couple of problems here. The decision diagram can grow exponentially. For example, for multiplier circuits, the decision diagram represents that circuit grows exponentially. Okay. Also, the size of the diagram depends on the ordering of the inputs, or the ordering of the variables. Okay. And can grow exponentially with a different ordering. Okay. There are also multi-value diagrams, of course, rather than binary. You have multiple values coming out of the node. Now, as I mentioned, as a result of one of my colleagues, Randy Bryan, that for any Boolean function, you need to reduce decision diagram, minimal size decision diagram. It represents that Boolean function once you fix the variable order. So the way that I like to look at decision diagrams, coming from the optimization world, is that it's a compact representation of a branching tree. And I'll show you an example. So here is a 0-1 inequality, which you can regard as representing a Boolean function. You plug in zeros or ones with the variables, and if the inequality is satisfied, the Boolean function has value 1, otherwise 0. So this is a branching tree. You follow all the branches, you can find out whether the inequality is satisfied. Well, to create a reduced decision diagram, first of all, you get rid of nodes you don't need. For example, here, the outcome of both branches is the same, so we don't really need a branch there. You get rid of that. And some of the subtrees are identical, isomorphic, so we can superimpose those without harm. And same thing here. Now finally, the identical terminal nodes can be identified. Then we have a reduced decision diagram. Okay. So it's a nice way of thinking about decision diagrams as a search tree in which everything, all the redundancy is removed. In the process, you get rid of a lot of the symmetry of the problem too. Coming from the optimization world, we know all about the problem the symmetry creates in solving problems. This is an example. Coming from math programming, I like inequality constraints. So this is a 0-1 inequality constraint, so that's that constraint. And the feasible set for this constraint is very complicated. In fact, it takes basically 117,000 bits of information to represent the feasible set in a minimal way. The PDB that represents it looks like this. It's fairly small. Unfortunately, if you have multiple inequalities and try to conjoin them, these things explode in size. In fact, if you conjoin two inequalities, the size of the resulting diagram is proportional to the product of the sizes of the two individual diagrams. That's a general result for conjoining two diagrams. So, it's not really practical for solving inequality constraint problems, but still, they have a lot of power to give you a compact representation of a feasible set. So, to represent a feasible set in general, we can get rid of the paths to 0 because those are the solutions that don't work, that aren't feasible, and just preserve the paths we want. Okay? We can also associate costs with the arcs to find the longest or shortest path, which will indicate an optimal solution. And I'll show you an example of that. It's a very simple idea. So the example I'll use for much of the talk is the stable set problem or the independent set problem. And that's the problem of selecting a subset of vertices of a graph to maximize the weight of the vertices in such a way that the vertices are non-adjacent. We're using non-adjacent vertices. So this is a decision diagram that represents that problem. So every branch indicates that you either exclude or include the corresponding vertex in the stable set. And every path corresponds to a feasible set, a feasible solution. So here, for example, we're choosing vertex 1 and 3. 1 and 3 are non-adjacent, so that is a stable set for the problem. And also, we can put the vertex weights on the arcs. Right, so now, an optimal solution of the problem is simply the longest path, the diagram. Okay? So if you can actually build a diagram for the problem, it becomes trivial. The longest path problem in basically network is trivial to solve. And this is an example. So if we have a decision diagram representation, the optimization problem is solved. Of course, the difficulty is that decision diagrams tend to explode in size, so we have to deal with that. Okay. Now, how do we build these decision diagrams? Well, there are many ways to do it, but it turns out in optimization, the most practical way, generally speaking, is a compilation method that works top-down. And we do this by associating a state with each node, much as you do in dynamic programming. So this is a connection with dynamic programming. So here we have the decision diagram I showed you a moment ago with states indicated. And what the state here indicates is the set of nodes that are still available to add to the stable set. So at the beginning, you have all nodes available. And if you select node 1, then you rule out its neighbors. 2 and 5, and only 3 and 4 are left. Whereas if you don't select it, then still all the other neighbors are available. So that's the idea. So now we can just build this thing in top-down fashion. So, and again, we select the options. Here we can't select vertex 2 because it's not in the available set. Occasionally, you will find that the corresponding states are identical. Okay, in which case you can merge those. It's called caching sometimes. Here's another case of identical empty set. So this simplifies the diagram. And continue in this fashion, and you get a decision diagram. Now, a point of confusion very often is that when you use this mechanism, you get a reduced decision diagram. So in this case, but not necessarily. Simply because you identify identical states doesn't imply that you have a reduced diagram. It depends on the state representation. In this case, we're just happen to be lucky. But in practice, we don't need a reduced diagram. It certainly helps, but we don't have to go into great effort to create a reduced diagram. Okay, now, how do you take this mechanism to build a practical solver? So these are the elements of a practical solver I'm going to show you. We're going to get rid of the exponential explosion by relaxing the problem using a relaxed diagram. We're going to use restricted diagrams, primal search and restrict, and we're going to use dynamic programming models and a new branching scheme. So these are the elements I'm going to show you as we go along. So what is a relaxed diagram? Well, it's a diagram that represents the feasible set and a superset of the feasible set. So if you have a diagram in which the paths include the feasible solutions, along with some infeasible ones, then the shortest or longest path in that diagram gives you a bound of the optimal path. So, coming from the optimization world, I can tell you that relaxations are absolutely essential to solving problems. Basically, we earn our salary by concocting relaxations. In programming, for example, we use cutting lines a lot. It gives you a tie linear relaxation. So this is the name of the game in optimization. So decision diagrams provide a discrete relaxation, which is something new. I mean, if you look at the optimization literature, like thousands of papers, it's very hard to find anyone who's used discrete relaxations, even to solve discrete optimization problems. There's some work very early, back in the 1950s, by Comrie, using number theory, but there's very little work in this area. So this is a new approach, I think, to relaxation. The nice thing about decision diagrams is that they don't even know whether the relaxation is convex or uses inequality constraints or linear, whereas in math programming, you need convexity, maybe linearity, to obtain a practical relaxation. So I'll show you how to build a relaxed diagram for this problem, same problem I showed you earlier. So we're going to start out, as I did before, using the state descriptions, the top-down compilation. Now, the tree is getting, or the decision diagram is getting too big. It's too wide. So I'm going to refer to the width of the diagram as the number of nodes in a layer. This is too wide, it's too big. So I'm just going to merge these two states, like that. Now when I merge the states, I'm going to introduce some curious solutions. Okay, so infeasible solutions. But the way I merge the states in this case is to take the unions of the corresponding states. That happens to work for this particular state representation. But in general, you use other, I'll show you other examples of how you merge states to get a valid relaxation. Okay, so we can do that. Maybe I'll do the same thing here. I'll merge these two because I don't want 3 in a row. And continue in that fashion, and now I have a relaxed diagram that's smaller. So I'll reduce the width to 2. And now there's a couple of paths here that indicate infeasible solutions. Okay. But all the feasible solutions are still there. Now the longest path gives me a bound. The optimal bound. And the bound is the holy grail of optimization, right? Finding a good bound. So is this going to be a good bound in general? Actually, it turns out yes. If you're clever in the way you merge these nodes, you get a good bound. And you could probably think, in advance, how you might merge nodes, right? You want to merge nodes that are probably not going to be along a good path. Right? So, in a part of the diagram that's not going to contain good solutions, you don't care about the accuracy of the representation, so you can merge those nodes. Whereas on part of the diagram in which the paths are good, long in this case, you want to keep the nodes separate. You want an accurate representation of the solutions. It's a bit like finite element analysis and weather forecasting, right? When people model the atmosphere with finite elements. If the weather is calm, you can coalesce and merge a lot of those finite elements. It won't make much difference in the weather forecast. But if in a hurricane, you want to have very precise representation of what's going on in the weather. So it's the same principle. Okay, there are other ways to create relaxations, and the next talk will show you one. That is, rather than simplifying the diagram, you start at the other extreme. Start with a diagram that represents all solutions, all possible solutions, all the Cartesian product of all the variable domains, and then start adding nodes to the diagram to make it more precise and more accurate representation. That'll come in the next talk. Okay, so the original application of this idea was to constraint programming, which I won't say much about here. So as you may know, in constraint programming, the name of the game is constraint problem. In constraint programming, what people like to do is to look at each variable's domain. It's the set of values that variable can take, and find out which of those values are consistent with the constraint set. Okay, so some of the values may not occur in any feasible solution. So those values can be removed, and that's called filtering. So in constraint programming, solvers typically look at each constraint and filter out values that can't occur in variable domains. And those reduced variable domains are propagated to the next constraint, and the process is repeated there. So it's a nice idea. It allows you to exploit the structure of every constraint and propagate each reduced domains. And by the time you're through with propagation, perhaps you cycle through a few times to a fixed point, and you have a smaller search space to worry about. Well, the difficulty with that approach, however, is that you don't propagate much information if you simply look at variable domains. Okay? So when you look at an individual constraint, you exploit its structure. And there are many ways to exploit that structure that's not captured in the contents of the variable domains. So one way to avoid that problem is rather than propagate domains, propagate a decision diagram from each constraint to the next. A relaxed decision diagram, so it's not too big. And that gives you an alternate approach to constraint programming. So that was the first application. Here, in fact, the first problem we looked at was multiple all different constraints, that is to say constraints that require the variable to have different values. It's also equivalent to a graph coloring problem, a classical problem in optimization. And you can actually reduce the search tree enormously this way. So here's an example of what happens as you allow the width of the relaxed diagram to increase. So this is the width of the diagram going up to 1,000. So this diagram probably has, maybe a few 100,000 nodes because the width is 1,000. And as the width increases, you can obtain a tighter and tighter bound on the optimal pattern. I should say, by the way, that a decision diagram of 1,000,000 nodes is not impractical. We can go up to 1,000,000 and process it fairly quickly.
Can you show anything from a theoretical standpoint of C?
So, yeah, there are basically no theoretical results, there are very few, as to the tightness of the bound. Okay. We don't know how to prove any kind of worst case or average case results of the bound tightness. Now, sometimes you can prove results of the size of an exact decision diagram. Okay. So, for example, in this problem, you can show that there is a variable ordering such that the width of the diagram increases with Fibonacci numbers. So there are results like that. But what we really are concerned with is the width, is the accuracy of the relaxation, not the size of the exact diagram. Well, that does give you a clue as to how to order the variables. Right? So you know that if you order the variables in such ways to get a Fibonacci result, then probably you have some indication of the quality of relaxation if you do that same ordering. So you have results like that. Yeah.
Have you observed a correlation between the best orderings for a relaxed diagram as an exact diagram?
Empirically only.
Okay.
Yeah, empirically, yes. A good ordering for exact tends to be a good ordering for a relaxed. And the reason for that is that we are exploiting dynamic programming structure as a problem. Okay, we're exploiting recursive structure. And I'll show you a bit of that at the end of the talk if we have time. So a good ordering in general is a good ordering for relaxation. Okay. Yeah, that's nice.
How come that there are these small jumps instead of decreasing monotony?
Per minute?
The small jumps that...
Oh, yeah, well, so since the relaxation uses a heuristic for merging nodes, there's no guarantee that allowing yourself to go one notch wider is going to improve the relaxation monotonically. It could actually get worse. Because when you allow a wider relaxation, we're going through and recreating the relaxation with a looser bound on the width. So in the accidental, mergings that happen in the heuristic, you could get a worse relaxation. So that can happen. Okay, so here we're comparing the quality of relaxation with state-of-the-art integer programming. So if you solve a problem with integer programming, at the root node of the search tree, the solver uses 50 years of cutting plane technology to create a good relaxation, as well as a number of pre-solved techniques and exemplification techniques. So we're up against a whole room full of geniuses in trying to create a good relaxation. Nonetheless, we're leading sequence, at least on this problem. Sometimes we don't, sometimes we do. This problem we're lucky to meet it. Okay, now you might ask, okay, yes, but how much time does it take to create this relaxation? Actually, it's much faster. You can, decision diagram relaxation can be quickly compiled, whereas generating all these cutting planes, separation algorithms, is time consuming.
For which kind of problems can you expect this kind of result?
Yes. Problems in which you can exploit the recursive structure. There's a kind of Markovian structure in the problem. We tend to get good relaxations. We need an intuition about whether the problem. So here, for example, this problem turns out that dense graphs are good for us. Sparse graphs are not so good. Okay, we have to develop an intuition. Okay, now there is a dual of the idea of a relaxed diagram, and that's a restricted diagram. In fact, you can take the diagram for a relaxed diagram for the problem, and then negate it. Okay, take the negation of that Boolean function, and you get a restriction. So that's one way to create a restricted diagram. And there are other heuristics. Now, in the optimization world, it turns out that at least half of the power of optimization solvers is due to so-called primal heuristic. That is to say, a heuristic that's used to find good feasible solutions that you can use to simplify the search. And that's done sort of on the side in parallel with the usual search tree. That's just been discovered in the past 10 years or so, 10 or 15 years. All the state-of-the-art solvers have incorporated powerful primal heuristics. Well, can decision diagrams compete with these primal heuristics? And the answer is yes. So I'll give you an example. This is a set covering problem. So we have 6 sets, and elements A, B, and C can occur in the sets, as shown. Okay. We want to find a subset of this family of sets that covers A, B, and C, that contains whose union contains A, B, and C. This is needed a programming formulation of the problem. Where X1 means that you include set 1 in the collection. Okay. There are 52 feasible solutions here. And it turns out the minimum cover has 2 sets. For example, the first 2 will cover A, B, and C, will contain A, B, and C. Okay. This is a restricted diagram for that problem. Okay, so all the solutions in this diagram are feasible with the set covering problem. It omits some of the feasible solutions because it's a restriction. It turns out that, so now the shortest path is going to give you an upper bound on the size of the minimum cover, because you're excluding some of the feasible solutions. It turns out here you get an optimal solution by taking the shortest path. We're lucky in this case. Okay. So there's a very simple heuristic for restricting a diagram. You simply throw out nodes that don't look promising, according to some fairly obvious criteria. Basically, there's a length of the path going through it. Okay. And you build it in that fashion. So this is a comparison of the quality of the solution decision diagrams versus what happens in the commercial solvers. So what we're showing here is the gap between the best solution we find heuristically and the value of the optimal solution. So we want a small gap. We want to get close. So this is what the solvers are giving us, and this is what decision diagrams. So it's, you see, somewhat better gap. And it turns out that the decision diagram is very simple to create, it's very fast. And you use the same method for every problem. Simple, one simple method. And you can see the comparison and the time required to create this primal heuristic. This is logarithmic scale. So it's quite a bit faster on this problem, but this is fairly typical result. Okay, now we're going to get a little bit meatier. Okay, how do you formulate problems for a decision diagram? So remember, I showed you the constructed decision diagram. You create a state representation. So every node corresponds to a state, and that tells you how to build the diagram top down. So what we need is some way to formulate a problem in terms of a state description, as we do in dynamic programming. So that's the art. Now, as you may know, dynamic programming is a very old field. It's been in the literature since the 1950s. guy named Richard Bellman created this field. And he thought he had a brilliant idea, dynamic programming. It's a great way to, to decompose a problem into stages. But unfortunately, in most problems, the state space, the number of states grows exponentially. This is called recursive dimensionality. And in practical problems, meaning the state size is truly astronomical. Like you have more states than atoms in the universe in a typical practical problem. So how do we deal with this? Okay, so in the literature, there's all sorts of ways to deal with it. Approximate dynamic programming, state-space relaxation, and so forth. So we're going to look at another way of dealing with this issue. So we're going to try to formulate problems using the state-space representation. Now, historically, this has not been the mainstream way to solve problems in the optimization world. Even though dynamic programming has some very nice applications, and approximate DP can also work, there's a couple of problems. One is that there's no off-the-shelf, software for solving the problem. It has to be hand-tailored for each problem. And secondly, you really have to be clever to approximate the state space in such a way as to give you a decent solution. Because you're searching the state space, and whenever you approximate it, you're losing a lot of information. So, it hasn't been the mainstream, although there's a lot of work in the area. Nonetheless, dynamic programming has a huge advantage, and it's the same as the one I mentioned for decision diagrams. You don't care whether your problem is convex, or linear, or has an equality formulation. You don't care. In fact, the cost functions and the cost to go and so forth can be represented by a black box, by an oracle. And so there's absolutely no conditions on the nature of the constraints and objectives, so long as you can formulate it in a recursive Markovian way. All right, so it has advantages and disadvantages. Now we're going to solve the problem not by searching the state space. Okay, we're going to use branch and bound in a way I'll show you. So in a way, it tends to sidestep this issue of the explosion of state space. Okay. Now, state variables that we're going to use are going to be the same that we use to create the relaxed decision diagram. So that's how you know how to formulate the states for dynamic programming formulation. All right, so this is the simple representation for the stable set problem I just showed you. Okay, this is the recursive formulation. So the state is the set of vertices of the problem that are still available to add to the stable set. Okay, remember, as I showed you before, go back. Back. Yeah, these things. This is the state, right? The set of vertices that are still available to add to the stable set. That's my state J. Okay. I don't want to lose you in the notation. So that's the state. Okay. So now you can solve the problem recursively. Do each stage, each level of the diagram. Okay. Then, given that you're at this state, you want to compute the maximum weight of a stable set. Given that you have this much, you have these vertices in the state. And what you do is just look at the possible vertices you can add next. You have a choice of these vertices that you can add to the stable set. Okay. These are the ones that are still available. So you add in the weight of that vertex, and then the cost to go. Okay. So this is the maximum weight you can achieve using the remaining available vertices, which can be put into the stable set. And those remaining are those that you now have minus the one you just added in all its neighbors, which you want a stable set. Okay, so it's a classical recursive equation for the problem. These are called Bellman's equations, after the inventor of dynamic programming. And there's a boundary condition and optimal value. You start with all the vertices. Okay, so that's a dynamic programming formulation. So once you get accustomed to this type of thinking, it becomes quite satisfying to think in terms of recursive structure. Now, we also need a way to relax the diagram. We relax by merging states. You might recall I mentioned that the way you merge states in this case is just to take the union of the states, the sets of the vertices still available. And this gives you a valid relaxation. So you've got to pick. You have to do two things to formulate the problem. You need a recursion, like this, and you need a way to relax, a way to merge states while preserving validity. Now, both of these are non-trivial. You have to think. On the other hand, it gives you an opportunity to exploit the structure of the problem, which is good. So we would basically get paid for exploiting problem structure, right? That's how we earn our living. Otherwise, you can just solve everything with off-the-shelf methods. Now, let me show you a couple of other problems, how they're formulated, and get the hang of this. So this is a very classical problem, single machine scheduling with duets. So we have a set of jobs. Each job has a given processing time. We're going to schedule these jobs sequentially on one machine. Okay? And each job has a due date. Some of the jobs will end up being late. We want to minimize the total tardiness with a classical problem. So the state here is very similar to the previous problem. It's just a set of jobs not yet processed. Okay? But we also need a second state here. The latest finish time of the jobs processed so far, or equivalently the finish time of the last job processed so far. Okay, you need two state pairs. How do you know that? Well, you just get the feel of it. You learn how to formulate problems this way. So this is the recursion. Here's our state. So we have these jobs that have been processed so far. This is the ith stage. The ith. We've scheduled I jobs so far. Okay. And this is the finish time of the last one we scheduled. So which job do we schedule next? We look at those who are available to schedule. These are the jobs that are not yet been scheduled. Sorry, those remaining. So we look at those that are remaining. We compute the tardiness that result, and we do schedule it now. This is tardiness. This is the finish time of the previous job plus the processing time minus the deadline. And if it's negative, we move it up to 0. It's just the tardiness. This is cost to go. So we can see how we change the state, we remove the job we just scheduled, we add in the processing time, the last finish time, and that gives our recursion. Okay, so fairly straightforward recursion once you see what the state looks like. And how do you merge nodes? Again, it's just a union. You take the minimum of these finish time to make sure we get a valid relaxation, a valid method. You've got to prove validity in each of these cases. Usually it's straightforward. Okay, so that's a classical problem. Now, you don't actually solve problems. No one solved the problem this way classically. The state space explodes. But now you can. In fact, in the next talk, you're going to see a solution of problems similar to this using state space representation that are actually quite competitive. Okay. Now, you can add all sorts of complicated constraints to the problem. Who cares? This makes the problem easier. So you're searching over a few possibilities and you can pick the next job. Also, the cost function can be as complicated as you want. It doesn't matter. You don't care. Because it's just an oracle that you're using to deliver the immediate cost, right? So this expression doesn't have to be a closed form expression. It can just be a black box. It doesn't make any difference, as long as you can compute it, of course. As long as you have a table lookup or something. Okay. Now this is a harder problem. So we're having a job scheduling problem with sequence-dependent setup times. Okay, so each time you go to the next job, you may have to reset the machine, and that depends on which job is next, how long it takes. So the famous traveling salesman problem is a special case of this. Okay. Well, this is harder. This is a problem with deadlines, time windows. So it's like traveling salesman with time windows, which is an incredibly hard problem. So in the textbooks, you'll see a model of something like this. You don't solve it this way classically because the state space explodes, but now you can solve it perhaps this way. Okay, so what is the state? It's the same as before, only now we have an indication of which job is the last one scheduled. That's that little L. We need to know that to make it Markovian. Markovian, of course, means that the state transitions or the costs depend only on the current state, not on previous states. To preserve a Markovian property, we need 3 state variables. And otherwise, the recursion is very similar. And the state merger, well, the state merger is a little more common. Now, here's a case in which you have to relax the diagram by complicating the state space a little bit. Sometimes you have to do that. So instead of having an indication of the last job process to create the relaxation, that state variable has to be a set of jobs that could have been last, instead of candidates for the last job. And then when we merge the nodes, we're going to take a union of those sets that could have been last, the last one process. Now we get a relaxation. So sometimes that's necessary. To relax the decision diagram, you have to modify the state description to get a valid relaxation. All right.
What if a job appears twice in the union?
That can happen. Yes. So it's a
Can
relaxation.
you get rid of one of them?
Yeah. So you just live with it. So the solutions in this resulting diagram can allow a job to repeat. If it's only a relaxed diagram, so that degrades the quality of the boundary. So that's okay. It's only a relaxation. We're going to solve the problem exactly by branching. But so we allow this slippage and relaxation. Okay, so I'm going to show you some computational results for some of these problems and 2 more problems. So I'm going to state the problems so you'll be prepared. One problem we have looked at is the max cut problem graph. So this is the problem. You have a graph. You want to partition the nodes into 2 sets so as to maximize the weights on the connecting arcs, connecting edges. Max cut classical problem. So the state we use here is actually rather non-obvious. It tends to work better for decision diagrams. You never use the state in dynamic programming because it's huge. State space is huge, but we don't care about that. We don't care because we don't search the state space anyway. The state merger is a little bit intricate. We also were looking at max 2SAT. Okay. So this is, you have a set of logical clauses, each containing 2 literals. We want to find the largest subset of clauses that satisfy. That's max 2SAT. Okay. Now, so I've talked about how to relax the problem, how to use a final heuristic, how to formulate the problem recursively. Now we're going to look at how to solve it using branching algorithm. Okay, so let me just indicate with a picture how we do this. I'll come back to this in a moment. So here we have, let's say, a relaxed decision diagram for our problem. So we kept the width small, limiting the width, and created a relaxation by top-down compilation. Now, the first few layers are going to be exact. And perhaps, as we get down to about this far, we can encode the problem exactly without making the decision diagram too wide. But at some point, it's going to grow so wide we start merging nodes. So let's look at the last layer for which the diagram is still an exact representation of the problem. And the rest of this is going to be an approximation of merged nodes. Okay? That's the idea. Now we're just going to branch on these 3 nodes. So each of these 3 nodes, we create a new relaxed decision diagram from here down. Okay. Now we can do the same, play the same game. In this one, we go to the last exact layer and branch again. Yeah, it's the recursive fashion. Now, what do we do with this? Well, we know the length of the path to the top. Okay, the shortest path from here to the top is just the shortest path problem. Then we add the length of the shortest path to the bottom, and that gives us a bound on the optimal bound. This part is exact, this part is a bound, Add them together, you get a bound of the optimal value. And this bound, let's say we're minimizing, it's a lower bound, can be used to prune the tree. So for example, if at the next node, it turns out that the bound we get is no better than the best solution we found so far, the best feasible solution we found so far. And there's no point in searching this branch. That's called branching bound. So it's done all the time. Something like A star. So you continue in this fashion. And again, each of these sub-decision diagrams, you can play the same game in a recursive fashion. You can do it first if you want, whatever works for you. So that's the branching strategy. It's quite a bit different than most branching strategies, which branch on values of a variable. And we're not branching on values of a variable anymore. We're branching on nodes in this relaxed decision diagram. It's a very different approach, and it has the advantage, I think. So this decision diagram, has removed a lot of redundancy in the problem. It's not necessarily reduced to a minimum, but it's because we have a state space merger. It's going to be a fairly parsimonious representation. So this gets rid of a lot of the symmetry. And as you may know in branching algorithms, symmetry is the bug of them. You don't want symmetry because you thrash, you search all these subtrees that are actually identical. Waste a lot of time. Okay. So that's the branching.
So, did you say that the decision diagram of a branch is constructed completely anew? Because we already have an approximate decision diagram.
Yeah, that's right. Yeah, so the way we do it is to start from scratch at this layer of the diagram and build a completely new relaxed diagram from there. Throw away the old one. Yeah.
But why would you construct then the remainder of the first diagram, the decision diagram at all? I mean, if you throw it away anyway.
To get the bound. That's the key. It gives you a lower bound. Yeah. And once you have that bound, you throw it away. Okay. Now, I'll just skip the slide, but there is something called state space relaxation in the optimization literature. This is very different. So my colleagues in operations research say, oh, you're just doing state space relaxation. No, we're not. It's very different. Don't believe me. Okay, so let me show you some computational results. Now, admittedly, these are on particular problems. Okay, but these are problems that are easily formulated for integer programming. So we're going to compare with integer programming solvers. So we're giving these guys, an upper hand here because we're solving problems on their turf, in a sense. And the problems don't necessarily have recursive structure. Now, people often ask, how do you know how to order the variables in a decision diagram to get a reasonable decision diagram? Well, if you just take a problem, off the wall, you really don't know how to order the variables. But if you have a recursive model in mind, then the recursion specifies a variable ordering. And this is what occurs to you naturally and intuitively as a recursive formulation. And that gives you the variable. So with these problems, there's no natural recursive model. So there's no obvious variable ordering. So basically, we just sort of take a random variable ordering. So that's the strike against it. But still, we can compete. Okay. Now, with stable set problem, we can't beat the big guys. They're a little bit short, fall a little bit short, because they cheat a little bit too. In any case, can't quite beat them on that problem. But let me show you some other problems. Okay. So this is the max cut problem I mentioned briefly. Okay, so you're partitioning a graph into two sets of nodes. So this is state-of-the-art integer programming, solution time versus decision diagrams. You can see it's very sensitive to the density of the graph. So with a dense graph, the kind of propagation we do in this compilation method is much more effective. So we get a much wider margin. This is max 2 set. Now, integer programming is not the best special purpose method for max set problems. You can do better than IP solvers, but it's not bad. You know, the results I've seen on MaxSat suggest that integer programming is sort of up there in the winning circle, although not the best for MaxSat. But after all, you know, we are proposing a general purpose method, not a specialized method for the problem. So we're competing with general purpose methods as opposed to specialized methods for that particular problem. This is how it looks. This is a performance profile. So this is the number of instances solved versus the time investment. So we're doing better. The crossover point down here. The problem's very easy. If you want to use existing technology. As the problem grows, the crossover point moves up. So easy problems, you want to use existing technology. For hard problems, you want to use decision diagrams. Now, how much does this scale up? Well, we don't really know. You know, we don't have that much experience, but there's a couple of observations you can make. One is that, you know, in many practical problems, the model, the inequality model for integer programming is actually too large to load into a solver. We have billions of constraints and variables and it's loaded. We don't have that problem because our model is just a recursion. Just a recursion. It's essentially a constant size model. Also, it turns out that parallelizing works very efficiently. We can almost linear speed up in parallelizing this branch and bound search. Whereas in integer programming, you get about 30%. That's to say, if you use 100 processors, you have a factor of 30 speed up in all clock time. Pretty close to 100% precision. Okay, as I mentioned, these problems so far have been natural problems for integer programming. So I think decision diagram becomes more competitive when the problem at the dynamic programming formulation comes naturally, including planning problems. The next topic shows sequencing problems like this, and so forth. Also, again, the objective function, the biggest complexity we want. So I'd like to talk about modeling the cost next, because that's a very nice feature of the recursive approach. It turns out that in discrete optimization, the decision diagram can actually represent any objective function, any conceivable objective function. Of course, the issue is how big the diagram must be to represent that function. But in many cases, not so big. It also turns out that we represent the function by putting weights on the arcs of the decision diagram, as I showed you before. You can do this actually in many different ways to represent the same function. Many different ways to weight the arcs to represent the same objective function. And you can take advantage of this. And find representation that gives you a smaller diagram. Okay, so here's an example of this. This is another set covering problem. The same one I showed you before. And here is the exact decision diagram for this problem. We're trying to, I guess it's not the same one. Yeah, so here we have 4 elements, and we're trying to cover all 4 elements by taking a subfamily of these sets. Okay. Now, this is a minimum weight that we cover. We want to find the covering minimum weight, where we add up the weights of the sets we use. So this, since each set has a weight, and we add them up, the objective function is separable. So all we have to do is whenever we choose a set, we just put the corresponding weight as the arc. Okay? And the other dashed arcs, which indicate we don't choose a set, have a weight of 0. Okay, so very simple to encode a separable function. The obvious way. But suppose you don't have a separable objective function. Suppose that the weight of each solution is given by some arbitrary table. You can't just add up the weights of the sets. Now, what do? How do you represent this with the decision diagram? So that's the problem we want to address now. The arbitrary objective function. Well, you do this. You do sort of the same thing I did before. Okay? You start with a tree, represents all the feasible solutions, and you put the weight of each solution on the corresponding leaf node, right? So if you take this solution on this path, the weight is 6, 0, 1, 0, 1, 6. Okay? So you start with the tree. Now, well, we start reducing the tree to get us a reduced decision time. The problem, of course, now is that we have these numbers that have to match, as well as the isomorphism we have to achieve. And that makes it very difficult to reduce the tree. In fact, in this case, we can't do anything. We can't reduce the tree at all. No, that's bad. But we can move these costs around. Okay. For example, what we do here is to look at the difference between these two costs and subtract off common elements. So we subtract off 7. So we get 0 and 1. We put that 7 up here to compensate. So it's equivalent, right? Equivalent. So you just keep doing this. And just work your way up. And now, you can see there's a lot of isomorphism, like these two, for example. So this canonical cost representation allows you to reduce the tree. Something simple. Yeah?
Is this going to be a lot more effective than turning the integers into a binary representation? Using that at the bottom of your tree?
So you would use a binary decision diagram, or?
So represent the number 7 using its binary representation.
Yeah, well, you still
Use
have
the
the
bits.
problem. You still have the problem of looking for isomorphism.
You would still face the same issue.
So it turns out in practice, this is just a practical observation, very often you see that the difference between these two choices tends to be the same in many cases across the board. It's by virtue of the structure of the problem. And then if you use this canonical representation, it allows you to reduce them. It may or may not work. You can try. And this is still a bit more complicated than the reduced diagram we got before with no costs. But it's not bad. So this is a general method. So there's a theorem here. Actually, there's a similar theorem that's been proved earlier by Scott. I think he's here somewhere. Yeah, there it is, yeah. So this has been observed before for different types of diagrams.
I got lost. So do you need to construct the whole diagram before you can do that, right?
Yeah, okay. Yes, good question, yeah. So, yeah, if we have to build a complete exact diagram and then reduce it this way, this is not going to be practical. Okay? So you have to take advantage of the structure as you write the recursion without actually constructing the diagram. You have to do it implicitly. I'm going to show you an example of that. That's an excellent question. Okay. You don't actually construct the whole diagram to do this. That won't work. Okay. All right. Okay, so this is the example I'm going to show you. So this is an example that appeared in a textbook that I used when I was very young, 100 years ago. The first problem you learn in inventory management, if you're in operations research. And it's a very simple inventory management problem. So the problem is you have a warehouse, you have several periods, and you want to stock your warehouse to have enough on hand to satisfy your customers in each period. In each period you have a certain demand. And you may want to buy ahead to take advantage of price fluctuations. And you have, of course, a cost for keeping the material in the warehouse as well, a holding cost. So that's the problem. So here's a little example. So this is a decision diagram that represents that problem. So what's going on here? So we have the states that we start out with nothing in the warehouse. Then we have a choice as to how many items to purchase, put in the warehouse. And this is the purchase cost, 4, 6, and 8. So if you look at the recursion here, the S is the current stock level we have in the warehouse. Then we're going to look at the purchase decision for this period. It's XI, how many items we purchased to put into the warehouse. So this is the holding cost that we're going to pay for the stock on hand, warehousing cost. This is the cost of purchasing the new items. Unit cost times the number we purchase. And this is the cost to go at the beginning of the next period. It's the best we can do from there out. Given this is going to be our stock next period. So next period we're going to have the current stock plus the purchase minus the demand. Okay, so very elementary stuff. Okay, and of course you notice this is linear. Right? The purchase cost is linear. The holding cost is linear, so it's a fairly restricted problem. However, you can relax some of these restrictions somewhat and get the same kind of result I'm going to show. This is to make it simple, very, very simple. Okay. So what's going on here? So, so on each arc here, I've indicated the holding cost and the purchase cost. Okay. So for example, here the warehouse is empty, so we have no holding cost, and we purchased 2 items, I think, to meet demand. So we have a total cost of 6. Here we have a holding cost because we have something in the warehouse. Holding cost is 2 per item plus the purchase cost. Here we have a holding cost of 4 because there's 2 in the warehouse plus the purchase cost. So these numbers here represent the state. The state is the number of items in the warehouse, row 1 or 2. And on the arcs we have the total cost, the total immediate cost, which is the purchase cost plus the holding cost. So now the shortest path with this network is going to be optimal solution. Okay, so that's the classical way to solve the problem, is find the shortest path. But now we're going to simplify the problem based on rearranging the costs of the diagram. So how can we rearrange? Well, you can notice that there's the arcs coming out of each of these nodes are very similar. They all go to the same set of states in the next period. Okay? And the costs are the same in their offsets. Right? The costs are all offset by the same amount. 3s. Just the absolute values are different. Okay, so you see this structure happens all the time. So what we're going to do first of all is we're going to have a change of variable to indicate the fact that we're going to the same set of states in this offset line. So that makes the destinations the same in the notation. We have a new state, and a new control. Right. All right, so that allows us to update the recursion, simple algebra. Now we're going to move the costs around by subtracting out the common element in each of these so that we only see the offsets. Okay. And then we add the offsets to the incoming arcs. So here, for example, this was 2, 5, and 8. Now it's 0, 3, and 6. And we put the common element 2 up here. Just add 2. You see how that works? And work out the algebra, you get a different recursion. But it turns out that the cost function now looks like this. It's a bit complicated, but it's just a simple idea that I show you all the time. All right, so the offset is this. These are the canonical costs. And now, if you look at these arcs coming out of each node, they're the same. They're identical. Same costs. Same destinations, they're isomorphic. New recursion, okay? So you can exploit this fact, and you can collapse the states of each layer. Right? So all these 3 nodes actually are identical. They have the same states coming out of them, the same actions in this case. So they all collapse into a single state. So you just have 3 arcs uniting a single state. So the state space is dramatically reduced. Now I didn't actually have to create this diagram to do this. All I had to do was to observe the structure and write the recursion accordingly. When you write the recursion accordingly, you notice the state variable actually drops out with the state description. See, before we had the state variable here. Now we only have 1 state in each stage, so this actually drops out. So you take advantage of this structure when you write the recursion, not actually generate the diagram. That makes the problem trivial. Yeah, it's interesting, you know, I mean, I've been in operational research for a long time. As far as I know, no one's ever observed this. It's a very simple idea, right? But it just falls right out of the concept of reduced to zero. You have canonical costs. Okay, now in practice, you're not going to have exactly the same states on every layer. You're going to have, you know, maybe some different constraints on the size of the warehouse and so forth. Some of the choices will be different. But to the extent that you do have this pattern in part of the diagram, you can exploit that fact. You still get a dramatic reduction in the size of the stations. Okay. Now, so that is the main material that I'm going to cover. Okay. I have another sort of conceptual piece of territory to cover here, but that's the main idea to talk about. Do you have any observations or questions before we move on and talk about it? Again, Scott. Whatever.
Okay. So this is like a compilation approach with decision diagrams, and it makes a little bit of like the Darwich work on decomposable D in and F and so on. So that you have a stronger version of canonicity than he does. Do you know any connections there?
Yeah, I think you know, I don't know all his work.
Yeah.
The connections are complicated.
Okay.
Yeah, there are connections, but I haven't seen the direct obvious.
So can you go back to the slide where you show a recursion? Just get this concrete. So so then I would say you take a compilation approach and you get these very beautiful diagrams, and I think it's very neat. But another way to solve this problem is to just crank through this recursion using the apply operation on ADEs. It's a very different approach.
Yeah.
So when do you think one works better than the other?
Yeah. So the apply operation has the advantage that you don't need an overall recursive structure. You just take the individual constraints and generate the diagram for each one, and then an apply operation. You get the diagram for the whole thing.
But you're eliminating as you go on, so you are doing DP.
Yeah.
Because on the NDP side, this is the only thing that we do, because we don't know how to handle probabilities in compilation.
Yeah.
We have to do the DP that way.
Yeah, I think there is certainly a class of problems for which that's an excellent approach. Yeah, because it depends on the nature of the problem. The problems that I grew up with that doesn't work so well, you know, I sort of think in terms of inequality constraints, it doesn't work for those.
Have you actually tried that approach with apply here? Would it just be a fun comparison?
We haven't done computational work with that because it just, and the problems that I've discussed here, that approach is completely fails.
Okay.
Yeah, so it's not good for these problems, but there, as you say, there are other problems for which it works fine.
Okay. I'd love to understand more deeply why, to be on point.
Yeah.
Yeah, maybe it's shortage in this question, but still, yeah. In the list, you show your lessons. Like I saw, for instance, these pseudo-Boolean functions. They were also hot some time ago, and then at some point they just saw that okay, it solves a couple of problems, but that's it.
Yeah.
How far do you think that VDs, that decision diagrams, are from this plateau, so to say?
Okay. Yeah, so a pseudo-Boolean function is a function of Boolean variables that has a real value or numerical value. So, first of all, here it's not just Boolean variables we're using, but it can be multi-value. So, Boolean methods actually used to work with the guy Peter Hammer who invented the field. Boolean methods work for a certain type of problem. They tend to exploit the induced width of the dependency graph, which I'm going to show in just a moment to have that idea. Yeah, so this is just a very different approach, I have to say, to the classical Boolean methods. They rely on It's true that they rely on a recursive structure to the extent that they exploit a small induced width. But there's no concept of a relaxed recursion, a relaxed diagram. There's no concept like that in Boolean methods. So I think that's the main difference. Okay, so we're using this relaxation idea to create a branch and bound solution approach. Complementary, it's like integer programming, whereas the pseudo-Boolean methods don't do anything like that. I think that's the main difference.
Okay, so the power would be basically in this relaxation capabilities that you have.
Yeah. Get clear?
What would be the behavior of decision diagrams and knapsack type problems?
We can't compete with the big guys on knapsack type problems. Now, the problems I showed you, like set covering, those are special cases of knapsack problems. We compete on those. But in general knapsack problems, with big coefficients and inequalities, we want to use integer programs. Also, in most of these knapsack problems, multiple knapsack constraints, there's no obvious recursion. Okay. However, very often, if you have a big practical problem, you know, if you rethink the problem in terms of its recursive structure, okay, maybe it's there, it just hasn't been exploited. There's no one can solve repeats. Then it begins to look more promising. Okay. So it really depends on whether the problem has recursive structure. But if you just take a knapsack problem off the wall, you know, like these problems you see in the benchmark sets, midline, all these things. All you see are the inequalities. You don't see the structure of the problem. In many cases, we don't even know what the problem is. So if you start with that, then we can't compete because we don't know the underlying structure of the problem. We can't explore it. Yeah.
It's mostly solved with approximations.
Pardon?
It's mostly solved with approximations.
Well, yeah. Of course, you know, the integer programming solvers rely on approximations. They rely on the linear relaxation. So if you don't know anything about the problem except the inequality constraints, you want to use an mixed integer solver. But if you know something about the problem, it allows you to exploit the recursive structure and try something else.
Thank you.
Yeah.
Are the techniques you presented implemented in some available software? For instance, the relaxed decision diagram, you compared the simplex statistics. Did you implement them in constraint programming software?
Yeah. Phil can tell you more about that because he's going to compare with constraint programming.
So what you just mentioned about the stable sets, max cuts, max two sets, all that code is available on the website, and I'll show in the next tutorial on the first title slide, and you can download it for free. And it also contains parallel code. And the constraint programming libraries are added to the IO CPU optimizer, which is also, we don't have the latest code on the website yet, but if you want it, I can send it to you.
Any questions? Yes, sir.
So, in cutting plane methods and so on, we reduce the set of constraints initially, but then find the right constraints sort of to add so that we can get better and better in terms of the quality of solution. Have you thought of similar ideas in decision diagrams, and we are making these relaxations and adding so we have done width relaxation and now we have got a bound. And then can we go back to the diagram and say, no, we don't need to expand some of the other parts because those are probably not going to lead to the better solution, but let us expand this part of the...
Yes, absolutely. That's the node refinement. Willem can talk about that, aren't we? Yeah, so he'll tell you about that in the next session.
John, you also have the separation procedure yourself.
Yes.
Are you going to talk about that?
So if you have a relaxed diagram and it turns out that the shortest path is infeasible, it violates some constraints. And you can modify the diagram to include the constraints that are violated, which is a standard idea in operations research. We use separated cutting planes. You can do that with decision diagrams too.
Can you say again what kind of property you have to prove to show that merging operation is valid?
Yeah, well, it's case by case. You sort of have to look at the state description and think about, how do I combine states so as to preserve the validity of the relaxation.
So
there's no one property.
What does it mean to preserve validity? So what?
Yeah, you just make sure that every pass through the decision diagram after relaxation, but sorry, you make sure that every feasible solution remains a path in the decision diagram. You don't exclude any feasible paths. So there's no one property. Look, you can prove some theorems, you know, for special cases, and you've got some necessary conditions. There are necessary conditions, but they're not really useful. I find, you know, you sort of have to take each case, one case at a time. Think about it. Okay. So I have a few minutes. Let me just show you the idea, okay? Maybe give you a little perspective on things. Everything I've done so far has been serial dynamic programming, where you have Markovian structure, one stage at a time. Okay, and each state depends only on the previous state. Okay? You can generalize that to the case where the actions available in each state depend on several previous states. Not all, but some. Several previous states. This idea has been exploited many different times over the years. The first I know of is non-trivial dynamic programming. It came along in the 70s. Bertagli and Ryoshi wrote a book on this. And it's surfaced independently, as far as I can tell, many different times. Okay, so it's a nice idea that people keep thinking about. So I'll show you the idea. Probably familiar with it too. So we'll use a set partitioning example. This is similar to a set covering problem, except that we want to take a subfamily of these sets that partition the elements. So here's an example. Okay, so the set's union contains A, B, C, D, but it's a partition. And here's another example, 3 sets. Okay, so this is the set partitioning problem. If you flew to London, then the crew of your flight was scheduled to the set partitioning model. Most of the airlines use it now, crew scheduling. Okay, so this is in the programming formulation. You have equality constraints. This indicates which sets are selected. Now, we're going to draw the dependency graph, a primal graph. So, two variables are connected by an arc if they occur in a common constraint. So here, for example, 1, 2, 3, 24 are connected, and so forth. This indicates the degree of coupling between the variables. There's a lot of structure in this graph that we can exploit. Okay. Now let's suppose that we're going to solve the problem by a search. We're going to enumerate values in this order. So let's branch up x2, we'll branch up x3, and so forth. And so we have this order. It's like a decision diagram order. Now, if you look at x6, it depends on 3 other variables. Okay? x6 occurs in common constraints for 3 other variables. So you can't determine which values of x6 are possible until you know the values of 3 other variables. Because those are the variables that occur in common constraints with x6. As long as you know the values of these 3 variables, you can determine which values of x6 are possible. So I'm going to indicate that with these lines in the red. Now, since we have to know all 3 variables simultaneously, then I'm going to add arcs to the graph, indicate we have to consider these 3 variables simultaneously. These are induced edges. Well, I include the induced edges to indicate that fact. So I'm connecting all the variables that are connected to x6. Now we go to x5 and do the same thing. So x5 depends on 3 and 4. 3 and 4 are already connected by the induced edge, so we don't have one. So we have to connect 4 and 5. And so forth. We run this same logic through all of the variables. Now we get the induced dependency graph, the induced edges. The width of this graph is the maximum in degree. In this case, it's 3. Okay, so the max in degree, or the width, indicates the complexity of the problem. The complexity is exponential in the induced width. It's a fundamental result of problem solving. This comes up all the time. So you can probably see what's coming, right? The state description is going to be like x3, 4, and 5. It's going to be one of the states, right? So the largest number of state variables that occurs in each state is going to be the complexity. So this is how you solve a problem by non-serial dynamic programming. So here I've indicated the state variables. Okay. We have 3, 4, 5, all part of the same state. These are the possible values that occur. Okay. And these are the possible transitions. So here we're choosing the value of x1. x1 can be 0. Okay. It can be 1. Here it goes to 1. So what I've done is indicate by these arcs in the usual way the transitions to the next state. Only now we don't have a linear order of the states. It's a tree rather than a path. So here we have a branch of the tree over here. Now, feasible solutions to the problem correspond to spanning trees that are corresponding to subtrees that contain at least one of each of these terminal sets. So you see we have a leaf here, a leaf here, a leaf here. Here's another one, a leaf here, and so forth. So as long as we pick one, we have a spanning tree that spans each of these nodes. This is a node, that's a node, that's a node, and so forth. Take those spanning trees, each of those corresponds to the solution. I'm going through this quickly because we're out of time, but I'm going to show you the idea. Okay, so this is the corresponding serial dynamic programming formulation. Here we have to have larger states to make it Markovian. So you see we can cut down the size of the state space, and therefore the complexity of the problem by viewing the problem as a tree rather than a single path, a single Markovian path. So this is the advantage of non-serial dynamic programming. Here the feasible solutions correspond to paths, of course, classical way. All right, now, this is the decision diagram that corresponds to the classical serial dynamic programming problem. It's almost the same as getting rid of the confusional states. Those, and so forth. Now, this is the decision diagram that corresponds to the non-serial dynamic programming solution. So you see there's a very close relationship. So you have a concept here of a non-serial decision diagram. It represents a non-serial dynamic programming structure in the problem. And now, you can solve the problem in a similar way. By looking for these subtrees rather than paths. So everything is the same except you're working with subtrees rather than paths from top to bottom. Everything else follows through the same way. Okay, so this is a way of exploiting more problem structure and reducing the complexity of the problem. Okay, so just to show you quickly, there's a systematic way of constructing this non-serial dynamic programming, non-serial decision diagram. And it goes like this. You look for cliques in the dependency graph. You might cliques over here. Okay. Maybe you've seen this before. Now, you create the join graph. Okay, so you join these cliques, and on the arcs, you indicate the variables that are in common between the two endpoints. Here we have x3 occurs in both of the endpoints. Here x2 and x3 occur in both endpoints. This is called the join graph. How that goes. Let's do that. Now it turns out that some of these edges are redundant. We can actually get rid of this one because we have an x3 path along here. Get rid of some of the edges. In fact, you can get rid of enough edges to form a tree. This becomes the join tree. The join tree captures the non-serial dynamic programming structure of the problem. Now we can use the join tree as a guide to creating the decision diagram follows the structure in a fairly straightforward way, which I won't go through today. This is the basic structure, and then you create a decision diagram by expanding each of these to represent the corresponding states. So there's a systematic way to construct non-serial decision diagrams based on the join tree of the problem. That's the point I'm trying to make. So it's another way of sort of expanding everything I've told you into a broader array of problem structures to exploit that structure. Okay, so I think we're just about ready for coffee break. Any parting questions or comments before we go? Well, if not, thank you for your attention and stay tuned for the next installment that's going to happen now.